Hello, gentlemen. So you're going to see a costume change. I did change our homework assignment because you do need some information from the exam video that you're going to watch for the lab section to complete the homework assignment I was going to originally assign. So I'll be changing clothes for the lecture, obviously, because I recorded it earlier. However, the plan today is I'm going to go over physical, chemical changes and properties with you. My plan is we'll do a lab next week and you'll get a chance to really identify physical chemical changes. It's a lot of fun. For your homework, you're going to read or watch a vaping video or article and answer some questions about it in an assignment. And then you're going to complete the particle level worksheet. So you're going to see a costume change. Those of you that have taken your test, I hope it went well. Those of you that have not taken your test, good luck. Make sure you have your notes, a physical copy, and a calculator and a pencil. Anyways, see you in the next slide. Costume change, go. When can you tell if chemistry actually happened? And I understand this is a crazy question because there are two types of changes. We have our physical and we have our chemical. Now we're focusing on the chocolate pie side. Chocolate starts as a solid. And then if I melt it, I add heat, it becomes liquid. So think about it on the hot summer day when you're holding a piece of chocolate and you get some of the remnants on your hand because it's melting. We have that melting point for chocolate, which isn't really that high in retrospect. So what's happening is we're going from a solid to a liquid. Now, what's important to note is that this is a physical change. Physical change can include when we're changing the state of matter. And if you remember, from your years in middle school and elementary school, there are three states of matter. There is solid, there's liquid, and there's gas. However, you really didn't talk about the logistics down on the molecular level of a solid versus a liquid. So, solid, right here, to liquid. Solid, think about maintaining a shape. So when you're maintaining that shape, your particles are actually, your molecules are really close together. They're not touching exactly, but they're vibrating next to each other. And they're vibrating and they're not moving from their spot. They're very much like, this is my spot. This is my city. I'm staying here. I am not leaving. And so they're next to each other. They got neighbors, but they're like, I'm never moving. Never, ever, ever. And they stay there. They maintain their shape. Which you can think about it. In this marker, I can't see them vibrating, but I can see the shape. I have a definite shape. This is my expo marker. So my molecules are staying in that area, and while they're close together, they're vibrating, they're just kind of hanging out, just like my chocolate. But when I add heat, specifically to my chocolate, the particles get a little excited, and they go, hey, I'm going to move away. And so they start moving away. They have a little space, but they have more freedom to move around. They're not, I'm stuck in one spot. This is my spot. They're now getting a chance to break apart and they're moving around. So think about like this. This is not an exact chemical change, but like a way to think about it. When you're walking in the halls with your friends before the bell rings and you're just kind of hanging out in the middle, you guys might be grouped up together and you're very like, we're having a conversation. I'm not leaving. This is where I'm standing. Because you really like to hang out with your friends. So you have a big group of people. They're in the middle of the hall and they're just kind of solid in a way. They're like a wall blocking you. But when the bell rings, which is like our heat change, they start separating and they move away. They start moving around from each other. And they might be in the same area because they're having a conversation, but now they're kind of walking. They're like, oh, I gotta go. Oh, we can walk to class together. And they have that space. And so it's kind of like before COVID, after COVID. You have that more social distance between the molecules, but while they're still hanging out around each other because they're a liquid, they're still maintaining some sort of shape. They aren't standing next to each other. They're not maintaining that shape anymore. They have some freedom to change shape based on where they're at. And so just know that on that physical level, it's just as easy as taking my solid particles and breaking them into a liquid. With a chemical change, however, it's not changing a state of matter. It's actually changing everything, like some of the stuff at the molecular level, and it's hard to reverse this change. So an example of that can be I have a silver spoon, and in the presence of oxygen, it becomes not so silver over time. It's rusting. I could, in theory, sit there and watch a chemical reaction. I think about, Lady Liberty. She's green now because she's rusted. She's a copper statue. And if you remember copper from pennies, it's not green. But over time of it being in oxygen, it's oxidizing, it's rusting. That's a chemical change. I could, in theory, watch a chemical change happen. I could watch rust form on metal, but that's not that fun. It's not really exciting. But I can view that chemical reaction, which is really cool. So rust is an example of a chemical change. And physical, I could really just take a piece of chocolate, warm it up on the stove, and there we go. I got my physical change. But now we're going to talk about some of the stuff and like where this can happen and why this happens. And so I want you to know about elements. So elements, these are things that cannot be separated by normal chemical or physical processes. So chemical, physical, I could, I want to add heat. That's not going to take an element and break it apart. It's not going to change it. A lot of these are going to be changed in a lab and in very, very ideal situations, ones that we could not replicate here in the lab, unfortunately. But they cannot be separated by normal. So they can, it's just difficult. But there are two types of elements that you need to know, and that is a monoatomic, which these are found alone and they're stable in nature. So I could look at the periodic table of elements, obviously, and I could look and see copper. Copper is a monoatomic element. They're found alone. So I don't have two coppers near each other like my diatomic, which we'll kind of talk about. I can just have like one Cu out and about, and it just can kind of exist like that. And it's stable, which is important. If elements are not stable, it can be a little crazy. Now, the other type of element, if it's not alone, is diatomic, and these are combined with itself in nature. So it's combined with itself, meaning there's two of them, and there's only 7 that actually exist. It's by itself in nature that is stable, and that is our hydrogen, so our H2, oxygen, O2, fluorine, which is F2, bromine, which is Br2, iodine, which is I2, nitrogen, which is N2, and chloride, which is Cl2. Typically, these ones are also found as a gas, which is important to note. But those are the only 7 that are actually diatomic. All the other ones are monoatomic, which is really interesting. So you'll never find like a hydrogen by itself. It's always going to be an H2 molecule if you ever found it out in the wild. Which you really wouldn't. But it's important to know that it's never alone. It's always got to have a buddy. Now, the next thing that we can talk about, though, is compounds. And compounds are when more than one when more than one type of atom is held together by chemical bonds. And so a compound is typically composed of molecules, and they're held together by those chemical bonds. So a single molecule right here that we can have is water. Water is composed of 2 hydrogens and 1 oxygen. So it looks like this, where my big molecule is my oxygen, and I have 2 little hydrogen hands in a way coming off of it. So they exist together like that. And that is a compound when it becomes joined by all the other water molecules that are around it. So it's composed of single molecules, but when they're all together, they create a compound. So think about it. I'm never going to find just one molecule of water. I always have a glass of water. So that glass is actually a compound of a bunch of single molecules. These, if I wanted to separate water, can only be separated by chemical reactions. So even if I do heat it up, I'm not breaking apart those chemical bonds. Chemical bonds have to be broken by chemical reactions when they're a compound. So when I warm water up and it's from a liquid, it actually just becomes a gas, but those molecules still stay intact. If I wanted to break them apart, I would have to do it through a chemical reaction. Mixtures are when more than one different type of matter, such as elements and compounds, are together. These can be separated chemically or physically, depending on what you're doing, and these are always through filtration, distillation, evaporation, chromatography, etc. So in examples, I could have water, and I could add some copper in it. So I add some copper in it, and maybe I want to mix them together. So I mix it up in a test tube, and the copper dissolves in my water. Now, I want that copper back out, but how do I do that? It's all mixed together. Two ways that I could do it if I wanted, there's actually several ways, is that I could put the copper in a bowl and I could add heat to it and I could evaporate all that water out. It becomes a gas, so it leaves, but the solid copper that I mixed in stays behind because it can't be evaporated. And so there's a way that I could physically get my copper back. I could do it chemically and use chromatography and like kind of extract them together. But there's easy ways to kind of separate my mixtures. It's kind of like when you have your Legos and you mix them up with maybe something else and you want a specific color. There's different ways that you can filter them out and get what you want out of it. So think about that with like mixtures. So they can be separated chemically or physically because I'm not separating the single molecule of water or I'm trying to break apart copper. I'm just trying to get one half of the mixture out. Now, we're going to go over a physical chemical change station lab next week, but this is important for you to know. Physical changes are always reversible. There we go. When I say reversible, I'm changing the state of matter. I'm going from a solid to a liquid to a gas. I could go back from a liquid to a solid or a gas to a liquid, or even go gas to solid, solid to gas. I'm able to kind of have a circle. I can go back, I can come forth, I can say, oh, I want to do this. Never mind, I want it back. Where chemical changes, which I'm assuming you're getting my drift, are not reversible. I can't break apart a water molecule and then try to force it back together. Because at the point of breaking, it will kind of do its own thing and go find somewhere else to join because it doesn't want to be alone like that. Much like my H2s, they want to join, I can't just have an H go off. It wants to be H2, it wants to be stable. And so it's going to go find another hydrogen. But I can't take two hydrogens and that I broke apart with oxygen and be like, get back together. I can't go back. So once I do it, there's no going back. Now, these are sometimes difficult to tell because you really need to understand them at a molecular level, which can be a little bit difficult, especially beginning, which is why we're going to go through the stations. But what is important to know is when chemical bonds are broken, because that's really going to help you. That's like your good question to know, because if a chemical change occurs, it means chemical bonds are broken. So if I break apart my molecule, I'm doing that with a chemical change, and it's breaking those bonds. They don't really want to go back together. Whereas a physical change, like I mentioned, when I'm filtering out my copper and my water, I'm not breaking those bonds. They're staying, the water's bonded together, the copper's doing its own thing. I might have mixed them up, but I can take them apart and be like, no, bonds were not broken. They're just kind of two things that were mixed, and I took them apart. But I'm not breaking bonds in a physical change. I'm breaking bonds in a chemical change. Chemical change can have some of the following good like pinpoint ways to see. These might have bubbles, they might have heat being expelled, you can have a mass change, a color change, pH change, which is like an acid or a base, and a precipitate formation. Now, a precipitate formation, if you've never seen one, is kind of difficult to see, so I have this video that's going to help us, and it's lead and iodide. They're combining, and you're going to see a precipitate formed. So right here, I'm going to add my lead 2 nitrate, and it's dropped into some potassium iodide. It forms a precipitate right here. This is my precipitate. Which is really cool because it means that there's like something left behind. Something new has been created and it's leaving it behind. So if I were to evaporate all this out, I would have that left over, which is really cool. And it comes up with this like brilliant yellow lead 2 iodide. So what's happening in this precipitate is it's adding into my potassium iodide and my lead 2 nitrate, and the lead and the iodide are actually coming together. They're very like they're breaking apart the bonds and they're coming together to make this new thing, which is crazy to think about because what's left behind is lead iodide. So I could go and filter this or evaporate out the potassium nitrate that's left behind, and I will have this new compound I just made, this new mixture, which is really cool. So that right there is a precipitate. So that's evidence of chemical change, which is crazy to think about. These are not always going to be evidence, because sometimes if I'm warming something up and I have a physical change and it's evaporating, bubbles are going to form. I could see a color change if I'm changing it physically. But it's important to note that a lot of these are going to be with chemical changes evidence. Physical properties. Always ask, is it a solid or a liquid or a gas? What does it look like? When does it change state? And what is its density? Those are some physical properties that you have that you can kind of identify, like, hey, this is going to be a physical change. Whereas physical changes are identify physical properties that won't result in bonds being broken. So properties of a physical, and then changes are making sure the bonds are not broken. This can be observed without changing your substance. So it can be shiny, bendable, color, conducts electricity, which is really cool. These are the states of matter. These are physical property. Solids are going to have a low Ke. They're closely packed and they can't compress. Ke means kinetic energy, just so you know. Liquid is fluid. It has a low kinetic energy. It's closely packed and it can't compress, whereas a gas is fast moving. It has high kinetic energy. Think about it, because it's moving around a lot faster, where these are kind of close together. It's far apart. You can't really have a shape for gas, and it can compress. So I have this video now, and it's just going through examples again. I'm going to post this on Canvas so you can listen to it. But just know, gas will assume the shape of the container and the volume. However, the particles are separated and they're going to move in kind of obtuse lines. And gas particles will change direction when they collide together. Yeah. Liquids have a definite volume, which, think about it, because I can measure the volume in a graduated cylinder, and the shape is going to be with the container. However, compared to a solid, these are still close together particles. They do have some space. However, they are close, and their motion is random, but because they're a liquid, they have some freedom with movement. Solids, they have a definite shape and volume, and you can see they're close together, like I kind of talked about. So gases, they'll collide with each other. It doesn't really matter where they collide. They can hit each other and then change direction. They're kind of like goldfish. Liquid, they can collide together, but they're always going to collide with people, like neighbors, neighboring areas. And so think about, like, my molecules. If it's water and they're H2Os, they're going to actually, like, kind of collide with whoever's near them. They're not going to collide with someone all the way across, because they're still kind of closely packed together, but they're not extremely closely packed. Whereas a solid is only going to collide with its neighbors because it's not moving. Chemical properties. Does it react with the air in our atmosphere? Does it react with water? Does it react with an acid or base? Does it burn or combust? Where chemical changes are identifying chemical properties will result in a chemical change. So a lot of chemical properties are a lot about reacting or burning, or is it doing something? Whereas physical, you're just making physical observations. When you're doing a chemical change, you're always making a new substance. So think about the lead iodide precipitate that I showed you. When I had lead nitrate react with the potassium iodide mixture, those broke apart. They broke the bonds between the potassium iodide and then lead nitrate to form lead iodide precipitate. So I made something new. I can't go back and change that. I can see a color change, a temp change, pH change, bubbles, and a precipitate form to really show me my chemical changes. Hi, I'm back. So your homework that you're going to be completing is you're going to complete the particle drawing worksheet. To do this, you're going to be using your Unit 2 packet and notebook from the notes we just kind of took to help you. Again, I just want you to try and get used to it. We'll practice this in class, obviously, but I do want you to try and figure out some stuff on your own and do a little bit of research by using those packets. You will then read and watch the vaping article. So the vaping articles, you will either get to watch the Science News for Students article, which is linked in Canvas, or the CBS News interview with the Juul CEO, also linked in Canvas. You will then answer questions in the vaping article follow-up assignment, And please be ready to discuss it when we're in class next. If there's any questions that you feel like you can't answer or you weren't sure what the answer was, do some research on it. However, you'll turn that in through Canvas again, under Notability, under Assignments. But other than that, if you have any questions, please let me know. Again, I wish you best of luck on the test if you haven't taken it yet. Wow. And those of you that have taken the test, I hope it went well. However, as a reminder, Unit 2 is a little bit shorter, so if you didn't feel confident on that test, don't worry. I'm thinking about making our next test less points, like less traditional exams, and maybe do something interesting, just to try something new. But until then, if you have any questions with your homework, let me know. Bye.